the workshop. So thank you again, everyone, for coming. Hope you have a good lunch break so far. So we're very lucky this year to partner with ICRA from Stanford as well as Turkey to come up with this Nothing Stands Still challenge. So in this after the session, ICRA will be presenting the results from the Nothing Stands Still challenge, and the winners will get to present as well. So you can take it away.
Thank you. Thank you so much. Hi, everyone. We'll start with the second collaborator of this challenge, which is Hilti. Michael, are you available?
Yes. Can you hear me well?
We can hear you. You are welcome to start when you're ready.
Thank you. Thank you so much. So welcome back, everybody, from the lunch break. My name is Michael Hellenberger. I'm working in the research department of Hilti. And I would like to give you a short introduction to Hilti, for those who don't know the company, also why we're doing these challenges. And afterwards, Iro is going to give you some more details on the challenge itself. And at the end, the two winners will present their approaches. So first about Hilti, we have been founded around 8 years ago in Liechtenstein. So we're based in Liechtenstein. It's a very small country next to Austria and Switzerland. And right now we're a multinational company with a turnover of over 6.5 billion francs. Our products include, so they range from drilling tools to demolition tools, direct fastening systems, measuring tools, also software solutions. And our latest addition is the J-Bot, which is a construction robot that's actually already operational on construction sites. It's a sealing drilling robot that we did. Our goal or our vision is actually quite simple. We want to make construction better. That means we want to have construction sites that are more productive, more safe, and more sustainable in the future. And for this, we invest in technologies like robotics, computer vision, and AI. And for this particular case here, what our goal is, we try to increase transparency on construction sites. So we're talking about really large construction sites where there's a lot of things going on, and we would like to develop tools and solutions for our customers that provide real-time feedback on the construction progress, what has been built correctly, what is out of spec, what about the project timelines, is everything in time. And for this, we use all available data sources, including, of course, also cameras and point clouds from laser scanners, for example. And this is where the Nothing Stands Still challenge comes into play, because, of course, in order to derive progress or the changes from laser scans, it's important to register them both in space, but as well in time, and that fully automatically. And so this could be, so such a registered point cloud is, of course, the first or the base for a large series of downstream tasks where we can then, create insights for our customers. So this challenge, we partnered with ICRA Romania, as you know. So thanks ICRA for providing this great data set, which is the base for this challenge. And it's really you're tackling this problem of spatial temporal registration. I'd like, so that's about why we're doing this challenge. Lastly, I would like to thank Qingdao. Thanks for hosting us again for the third time, I think, already this year in total. It's always great. It's a great workshop. It really fits our goals. Also, thanks for Sun Tao. I think you made sure that the challenge was running so smoothly as it did. You answered all the questions. You made sure the evaluation was going. And of course, also thanks to all the participants who downloaded the data set and used it. And of course, the data set is still online and available. So please feel free to download it and see for yourself. I'd like to hand over the stage to ICRA. She will give more details, and she'll also announce the winners. Thanks all for your attention. I'm really looking forward to the winner presentations.
Thank you so much, Michael. I will continue now to discuss a bit more about the challenge. Let me share my screen for our online participants. Okay. Good. So welcome at the challenge. This is the team members that participated in actually making this happen and being able to bring to you the evaluation server, be there to answer your questions, be there to help with deciding the winners. And particularly a big thanks to Tao, as Michael said, because he has been the one making all the work happen for this. I was just there telling him what to do rather than doing everything. So a big thanks for him. If it wasn't for him, things would not have happened. And of course, a big thanks to Michael and Artie for creating this collaboration and bringing the Nothing Stands Still dataset to this workshop, and also Jing Dao and the rest of the organizers of the workshop. As Michael mentioned, this dataset is part of the effort of Nothing Stands Still, a spatiotemporal benchmark for 3D point cloud registration under large geometric and temporal changes. And you can see the authors that have been part of this effort. The name, for those that do not know, is inspired by a Greek philosopher, an ancient Greek philosopher, Heraclitus, that said that everything flows, nothing stands still. And essentially that there is a lot of temporal change. Now, why it's important to understand the change in construction, and why do we need to have a better understanding of what happens in our construction? I will just give a few statistics for those that are not familiar with the field. 50% of the rework, 50% of construction cost increase, essentially additional, like 50% of what it's additional to our initial estimate is used for rework, which means, and a big part of rework is due to things that we have not constructed correctly. So ideally, we want to make sure that we know where we have constructed them and how. In addition to that, there is a lot of safety issues, particularly in the US. 20% of all occupational fatalities, not even injuries, is in the construction workers, where essentially we had in 2020, 976 fatalities, which is quite a large number. Going away from that, we can also consider how 95% of non-hazardous and demolition waste is actually recyclable or reusable, which means an understanding of where things are, how are they located and connected with other elements is extremely important when we are talking about sustainability and reaching sustainability goals in the construction, which is a very wasteful, in that sense, sector of industry. So when we started looking into, okay, maybe we can use existing data sets to create algorithms that can understand what is happening in construction sites over time, which means we need to know these large geometric, semantic and topological changes that are happening. And we looked into the spatiotemporal 3D point cloud datasets, and we found that there's small scale that restrict themselves to a room or a couple of rooms, and they're mainly capturing changes that have to do with daily human interaction, which means moving some furniture around or removing or adding furniture into the room. There is also work happening in the 3D spatiotemporal registration, of course, but it's mainly for self-driving datasets and applications. They either focus on pairwise and multi-way registration. However, they are dealing with small changes happening in the scene, right? So a car goes a little bit ahead, maybe a biker passes by, a pedestrian, but the main structure of the scene remains as change, which means that first of all, we need a data set because the current spatiotemporal data sets we have are not enough. And second, can our current methods robustly perform in environments that underwent large changes? And that is why we created the Nothing Stands Still data set and benchmark. And from our paper, we realized that existing methods cannot robustly handle this noise, this data. And that's why this challenge is great to see what we can do so far with new methods that are developed for this particular domain of data. A brief introduction into the dataset, but I do ask you to refer you to the paper if you wanted to learn more about the dataset. We have 6 main construction sites that we have been capturing over time. So we have multiple scans for each of them, with a total area of all of them to more than 50,000 square meters. And as I said, we have different temporal points for all of these construction sites. Here's just a small crop of an entire scan, and you can see how it changes over time. So from an empty space here, we go to starting creating the interior layout of the rooms and then making it look even more complete. What I did not mention is that we are not looking for the construction sites for the point that they are just getting created and you set the foundation and then you put up the structure. We are looking at it from, we have the main structure constructed. We are looking at understanding how the interior layout is being done. Here are some more examples for area 1, stages 1 and 3. So there are 3 main stages here. And you can see how you start from a very empty space. And then on this side, you have a lot of materials and equipment being located. And on this side, you actually see that from 1 to 3, you already have all the walls and the interior room created. Now, the temporal difference between the stages is not set. We're doing it every time there is information that will be hidden behind surfaces and not be visibly accessible anymore. And to do that, we communicated with the contractors of the sites every time. Here's another example where you can see 5 and 6, where the changes are more small in this case for another building, where you have the interior layout created with these different studs here. So you start having the wall separation. And over here, it is even more complete with even some built-in furniture. And in this side as well, you start by having this, and then you have the built-in laboratory on this side. Here is another example. But you can see more information on our website and on the paper. Very briefly, and I will not go into detail about that, here is what the dataset, how the dataset was created. So we scanned a lot of these construction sites, and unfortunately, for reasons that I don't want to really delve into, we could not have access to the raw data from the device that we used. So we ended up having 3D reconstructed meshes from which we are going to sample the information, the point clouds, and simulate the actual raw data in the similar way that the device would do. And in order to do that, we sampled first the location of scanners on these floor plans, on these 3D meshes. And from there, for each of those potential scan locations, we are going to recreate how the device would actually make a point cloud. And we are creating a depth panorama, and from there, a simulated point cloud. Now, the device we used was based on RGBD cameras, and specifically the depth is the Kinect sensor, which means we have added the statistical noise of that device as per literature. And now we sampled many of those point clouds, and we actually split the data set into 3 different generalization capabilities. And for the challenge this year, being the first time we do it, we started with only the original split. The original split is per literature of 3D point cloud registration, where essentially you sample training and testing data from all scenes all over time, right? So you see the red dots are training data, the green dots would be test data. So in every possible area and temporal point, you have both training and testing. We also have other ones which we are hoping to introduce next year that show different generalization capabilities, but I will talk about it in a second. Now the task is about multi-way registration of 3D spatiotemporal point clouds, where essentially you have multiple fragments over time that could have some overlap or not. And then your goal is to be able to register them all together into one coherent spatiotemporal 3D or 4D map. And what we give to the participants is a pose graph where we've shown what are the edges between the pose graph, and they have to find what is the in-between pose, the global pose of those fragments. Since this is how the spatiotemporal pose graphs look like, so you cannot see very well maybe because it's too small, but all these little dots over here are actually scans, and then edges are created between to create this pose graph. And given that we do not have odometry edges, these were created based on the minimum spanning tree. But again, I refer you to the paper for more information on that. And we essentially had in the test set, not the training and the validations, which have way more. In the test set, the total nodes, the total fragments that the participants had to register was more than 4,500 nodes. So we're talking about a lot of scans that they have to put together. You can see even here like how some of them are super dense. As metrics, the main metric that we judge the winners for the challenge is the global RMSE, but also we calculated the pairwise RMSE, the recall, average rotation error, and average translation error as well. And what is most important is that the test set was hidden from the participants. Hence, we had an evaluation server on which people could submit their results, and the evaluation server was able to calculate these metrics. The challenge was up for about 2 months. Hopefully next year, now that we have set everything up, will be even more faster available for participants. And at the end, we had 8 submissions, which again, such a feat for that short amount of time. Of course, nothing was all rosy. We had our challenges, and one of the biggest challenges we had to, one of the biggest errors that came up, and thankfully participants, and actually the first team that won the challenge was able to point, is that we judged all of the global RMSE based on an anchor point for each of the areas, for each of the 6 construction sites, which would be this one. However, the evaluations, and that is based on the nodes and the list of them and the order of them into the results. However, the evaluation server was actually shifting the order of those nodes. So we ended up having some weird instantiation of the anchor point, which was sometimes here, sometimes here, sometimes here, sometimes here. So the participants were getting some big errors with respect to ground truth for the test set only, because offline for the training and validation, they could see the correct scores. We were able to fix that and do the evaluation based on the actual correct anchor node. But now we know, and it won't happen again next year. And here are some of the challenge results. I couldn't put all submissions online because some decided, because being part of companies, to not showcase the results and withdraw from the challenge at the very end. But you see here, based on the global RMSE, we started with some teams having quite a large error, but we see that the first team that won was actually to bring it down to almost 5.6 centimeters deviation from the ground truth, which is such an amazing result to see. And you can see here the rest of the errors as well. But the main that we judged the challenge was the global RMSE. And now it's time for the challenge winners. And I will start with those that took the second place. So I want to congratulate Yinchan Chang, Liang Lu, and Professor Jia Pan from the University of Hong Kong for achieving the second place in the challenge. Congratulations. The winners will present their methods shortly after I finish. And here is the first winner of the challenge with those amazing results, the team of Hyang-Tae Lim, Jingdan Shi, Yun Chang, Lucas Schmidt, and Professor Luca Carlone from the Spark Lab at MIT. Please congratulate them. Okay, and with that, I want to conclude with one last slide to tell you what's next about the challenge, and then I will let the first team present their method. So the first thing that I think we should do is to add all splits that we have of the data set, because the original one is essentially the easiest of the splits, since we are training and testing from the same area. We also have the cross area split, which allows us to check if we are generalizing across different construction sites. And then the cross stage one will allow us to check if we're generalizing across temporal changes. So we are thinking of next year adding that and deciding on maybe an average score for all 3 splits in order to decide the winner. Lastly, we are now working on adding semantic information on the dataset. I hope to have it by next iteration of the challenge, but you know, fingers crossed, you never know how it goes, but it is upcoming, it is coming, in order to be able to unlock more vision and robotics tasks, regardless of the challenge itself. And for the challenge, we were thinking of semantic registration also as a possibility of a task coming up. And last, I want to tell you, if you have any other suggestions on things that you would like to see based on the data set that could potentially be task of the challenge going forward, please let us know. We'll be very happy to hear any of your suggestions. And with that, I want to thank again the entire team that worked on the challenge. I want to thank the workshop organizers and of course the winners. And I will see you next year with the challenge results.